So the fundamental question is, what would have happened without partisan intent? And we want to assess the consequences of policy through sampling. The work that we're going to tell you about, it's kind of caught on in the courts. There's been a long history of people attempting to claim that maps are unfair for a while. This framework that I've just presented to you has really caught on as an effective framework for discussing and understanding when a map has been drawn with a nefarious intent. So there's been a number of court cases we've been in now. And there's a number of other groups that have sprung us as well, at Tufts, at CMU, at University of Michigan, Stanford. I'm sure I'm missing some, but this is kind of caught on as a really interesting and new field. So before I kind of go into, well, how do we interpret the maps? I just want to sort of lay a very simple groundwork first. So we're going to say, like, what are some of these policies that can go into it? Well, we can demand that we have connected districts, that we have compact districts, we have roughly equal population. Maybe there's certain protections for groups. So the Voting Rights Act can apply, which will ensure that certain minorities get significant enough representation so that their votes aren't diffused throughout the districts. There's also things like preservation of communities of interest, which can mean counties or municipalities, or just neighborhoods, or something a bit more vague, and things along these lines. So if we have these four actual plans that people have drawn, we want to understand, okay, well, which of these are reasonable, are in some sense fair, although I'm going to put an asterisk on that word fair because that's more of a philosophical statement, and we're going to turn this into a statistical question. And we want to probe these plans. We want to understand the behavior of these plans and understand the behavior of these plans in the context of these policies that we're mentioning. So the game is to compare maps, as I said, through the MCMC sampling. So we're going to take these, we're going to generate a whole bunch of alternative plans. And this is we're going to come up with an ensemble of maps from here. And there's a bunch of things that we can do with these maps. The first thing that we're going to do is the following. We're going to take some historic vote counts, and on each one of these maps that we generate, we're going to use those historic vote counts, and we're going to say, well, how many Democrats and Republicans would have been elected under these maps? So under this current histogram that I'm showing you, there's 13 seats up for grabs. Excuse me. There's 13 seats up for grabs. There's a couple of, and what this histogram is saying is saying that, in 35% of the plans, 6 Democrats would have been elected, and 42% of the plans, 7 Democrats would have been elected, and so on and so forth. There's an immediate takeaway here, which is that without changing a single vote, only changing the way that vote is interpreted, you can go from electing 4 of 13 Democrats to 9 of 13 Democrats, which is essentially the same thing as saying 9 of 13 Republicans to 4 of 13 Republicans. So the ability to draw these lines is a tremendous amount of power. It's a tremendous amount of political power. So if map drawing seems like it's something that a bureaucrat would do behind closed doors, which they do, and it never see the light of day, you can see why this has caught on in the last decade as such a pivotal and kind of in the news cycle topic, because there's just so much power involved in it in terms of how we're represented. So this histogram gives us a sense of, okay, well, what happens under this vote counts? How many Democrats are elected under these vote counts? And we can take those 4 plans that I showed above, and this judge's plan was made by a panel of bipartisan judges, 5 retired Democrats, 5 retired Republicans, and they got together and they decided, we think this map is pretty good. There was a remedial plan that happened in 2020, which behaves basically essentially the most in terms of the most typical outcome. And this remedial plan was a fix on what happened in 2012. Well, really what happened in 2016, and the 2016 plan was a fix on what happened in 2012. This 2012 plan was deemed by the Supreme Court to be a racial gerrymander. This 2016 plan said, okay, well, we're not going to racially gerrymander anymore, but what we are going to do is we're going to partisan gerrymander. And for those of you who have heard the famous quote by Representative David Lewis, this is the map that he said, I had them draw a map that would elect 3 Democrats and 10 10 Republicans because I didn't think it was possible for them to draw a map that would elect 2 Democrats and 11 Republicans. So it was very intentional and very out in the open partisan gerrymander, but they were kind of really, it seemed like it was really flaunting and challenging the legality of these partisan gerrymanders. Under a different set of votes, which goes more Republican, so this is the Obama vote, this is the Trump vote, or those years, there's a shift towards the Republicans. You see that the Ensemble is now most typically electing 5 Democrats. This is a good thing in our mind, because as you would hope that in a democracy, as the preference towards a party changes, that party starts getting more representation. But if you contrast this with the 2016 and the 2012 maps, you see they're okay, they do shift by 1. But we'll see in a moment that they're largely going to be stuck, and they're still very much at the low end of what you'd expect. So those 2 elections. But you may want to say, well, what happens over a range of elections? So these are these same histograms that you saw in the previous plot, except now they're contextualized in the statewide vote share that the Democrats and Republicans received. So here, what you're seeing is the, under the governor 2012 votes, this was about 44% of the vote went to the Democrats. As the Democrats gain more votes under the Ensemble, they start gaining more seats. Under the judges' plan, they gain more seats, and under the remedial plan, okay, they're largely stuck at 5 and then start gaining some more seats. So there may be a bit of an issue with responsiveness here. We'll leave an asterisk there. But if you compare this with the 2016 plan, this is very firmly stuck at electing 3 Democrats, except for this one exception here. And so this is kind of showing, there is this kind of extreme behavior where it's really robustly and continuously electing almost exactly as David Lewis, Representative Lewis, suggested it would behave. We can animate this process, essentially smoothing a histogram from this low end to this high end, and see what happens. So you see, when under a low Democratic vote fraction, the Ensemble is fairly typical of the enacted plan is fairly typical of the Ensemble, but then it just stays stuck where the Ensemble continues to react and grow its Democratic vote share. And only under very large shifts, under about 52% of the vote going to the Democrats, is finally it start breaking, but it's still lagging behind. And only when we get to about 55% of the Democratic vote share, which in North Carolina hasn't happened in a long time, do we finally see this catch back up and start behaving typically again. So that was the thing I just showed you was happened in 2016 and was the remedial phase of 2020. This is what was attempted to be passed in the most current cycle. So this is the CST 13 map. You'll see this lagging behind the Ensemble. This was very recently overturned, and there is a new map in place now. But this is kind of just, the fight continued despite the courts intervening during the last decade. And the final thing I just wanted to talk about is that when we get to state legislatures, it's not just about maybe maximizing the number of seats you have, but it really becomes about power. If you get half the seats, you get a majority. If you get, roughly 2/3 or however the supermajority is defined, you get a supermajority at that point. And that's what happened in the House. And so this was a kind of a very similar case that happened in the last cycle, where again, we're going to see these histograms grow, and this overturned plan is just going to lag behind. It starts as typical and is going to start lagging behind the Ensemble. And in fact, it's going to start getting stuck electing a supermajority, where now almost all of the plans are breaking that supermajority. Finally, it breaks free. And I'm just going to drag this up to accelerate it. Here you see that that every single plan in the Ensemble we see breaks the Republican majority, whereas the overturned plan is still electing a Republican majority. One of the things we really like about these methods is that they decouple the partisan impacts of the maps from the geography of the maps. So you might intuitively expect that if the vote goes 50-50 under a fair map, half the seats should go to each party. But if we look at a 50% Democratic vote fraction here, we see that in the Ensemble, there's no map that's electing a Democratic majority. This is the geographic effect. This is the way that geography of districting interacts with the vote pattern. And this is life. I mean, if you don't like this, you need to do some, you need to add something to districting, or you need to do something other than districting. But the difference here is that the overturn map is still on the extreme end of the ensemble. And so really what we're doing is we're decoupling the geographic effects from the partisan effects. And this is one of the things that has made this such a difficult problem to tackle, is because whenever somebody has claimed that a map is unfair, they've said, oh, well, it's really just because Democrats are packed in cities or something like that. And we're capturing those effects with this framework. There's one more point I'm going to make before I hand it over to Jonathan, which is if you were following gerrymandering early in the decade, and maybe even, or I guess early last decade, and maybe even up till now, there's still this public perception that if we only sort of constrained the way in which we drew maps, that would fix all of our problems. The state space is huge, and so this is an example where in 2012 there were these horrible looking districts. You look at this and say, yes, this is a no. You know it when you see a gerrymander. But it turns out this new 2016 map looked quite nice. These districts look fine. There's nothing that really sticks out about them as horrific gerrymanders or anything. But politically, they behave the exact same way as these 2012 plans. The point of this is that for the most part, we don't see, if you come and say, well, let's make sure the districts are compact. Well, let's make sure we preserve counties. That's not going to save you from gerrymandering. It may rein things in a little bit, maybe. I mean, this is kind of all open, but at least in practice, the constraints people have attempted to put on form have not really limited people's ability to manipulate these maps for their own gain. And it's just, so we should not be thinking about the classical gerrymandered map as these ugly districts anymore. We really need to think about it as the intent and the behavior of how these maps perform. So Jonathan, I'm going to hand it over to you.
All right, so so far Greg has really emphasized the seat count, and I want to kind of dive in a little bit more and say that we really need to think more about just not who wins, but how they win, and that's really important for understanding the structure of these maps. So Greg, go ahead, next slide. So what I'm going to do here is I'm going to take that one of those maps, that judges map that Greg showed you, and there are 13 districts, and I'm going to order them from most Democrat on the far right to most Republican on the far left. And I'm going to order them, so the horizontal axis here is the fraction of Democratic vote count in each of those districts. So Greg, go ahead to the next one. So that means the one on the far left is the most Republican, and only had 35% vote count, Democratic vote count. Next one. The next one is the next most Republican, 40%, next one. And then the far end, we have a 66% Democratic district, okay, and now go ahead one more. All right, and so from this representation of a particular election for a particular districting, you can immediately read off who won, right? You can, all the ones that are above the 50% line go Democratic, and all the ones below the 50% line go Republican. But we're going to be able to get a lot more information out of this. So go ahead and put the next up. So what I've plotted now is I've plotted these box plots, and each of these box plots is the marginal distribution of this very high dimensional distribution on the order statistic, where I've taken for every map, I've ordered it from the most Republican district to the most Democratic district for a certain election. These are two particular congressional vote counts. And now I've centered that histogram using, I've put the box plot. So inside of each box is the 50% of the data. And then these whiskers give the maximum. And usually we actually put some tick marks on here, but they're not here. And we've drawn a line, this yellow line through the median. And what you see is that this judge's plan, this bipartisan group of judges, their plan, it tracks reasonably well the median. It goes outside the box, the 50%, but not so bad. Greg, the next slide. But now, go ahead, just go on to the next one. So now if we go ahead and add the actual maps that we used in the 2012 and the 2016 elections, what you see, these orange and this purple map, you see that there's this dramatically different structure, right? You see that the three most most Democratic districts have way more Democrats, and then the next districts have way less Democrats. So go ahead, Greg, click. So this illustrates what I'm saying. So this is what people refer to as packing and cracking. And this is a really important thing to be able to actually get in and see the structure of these maps. So we can actually see that, yes, The way this was achieved was by putting a lot more Democrats in the most Democratic districts and thereby depleting them in the next most Democratic. So they took districts that would have been in play typically under these kind of elections and removed them from being in play. And this huge jump between, you know, the I can't quite read, the fifth, the fourth, and the third most Democratic district, this huge jump is exactly what leads to this non-responsiveness that Greg showed, which is really what we think is problematic. You know, there's this saying that elections should have consequences, and the fundamental fact of a democracy, a functioning, no matter what party you support, there should be this idea that when people change their opinion enough, the election outcome should change. And what this ensemble does is it lets us take into account the geography and where everyone lives to figure out what change we should expect to see when we change a certain vote count by a little bit. And we see that this green line just very, very, in a very kind of general, nice way, changes its outcomes as it's shifted up and down. And these orange and purple, the ones don't. Greg, go ahead. All right, so yeah, just go ahead. Let's just skip that, yeah. Oh, actually go back one more. Actually, I wanted to say something, sorry, Greg. So the thing to see here is, you know, do these court cases matter? Yes. You know, the yellow lines are actually the maps that replace those maps because of a 2008 court case, or we testified using exactly the data I've shown you. And you see that although they're not perfect, they're significantly better. They track significantly better the structure that one would expect in the state. So they were much better maps than the maps that were used in the 2016 and 2012 elections. Go ahead, Greg. And here's making that exact point I said before, that the fact that these purple and orange dots on the left panel don't move, they're almost stuck at 3 seats, is exactly because of this huge jump. Because as you shift this map up and down, it's essentially like shifting the purple curve up and down and seeing how many dots fall across the 50% line. So go ahead, Greg. All right, so this is just making this point that, you know, this fundamental idea that we should look for responsiveness in elections. I think that's actually more important than competitiveness, but this idea that this kind of nonpartisan idea that elections should have consequences. All right, go ahead, Greg. All right, so kind of Greg did a little bit. So, you know, this is a data science group, so there's a bunch of parts of this. Part of this was how do we analyze this data? How do we show it? But now it's part of this thing about generating the ensemble. So go ahead, Greg. So you might say, you know, somebody might just say, let's generate a bunch of random maps. And I want to first of all convince you that's rather sloppy language. And that's not, you shouldn't be satisfied with this. But the first thing you might do is, which is what any good Bayesian statistician would do, one would just do kind of an Ising flip. That is to say, here's Iowa. To change the district a little bit, you would just pick any of the edges that are highlighted in the upper rightmost panel. Those are the conflicted edges. You pick one of them randomly, that one there, and then you just shift the color randomly across it. And that would be a move. That would be a way to slowly evolve the boundary. That's one way. Go on to the next slide. A different way was a really nice, that's a very local move, a much more global move, which was a nice idea that Daryl DeFore, Moon Duchin, and Justin Solomon had, which is this idea of merge split. So what you do is you take 2 districts, let's say the orange and the green, you make them into one district, then you draw a random spanning tree, a uniform spanning tree, let's say. So that's a graph that covers every vertex in that graph, which is the center of each of these precincts, but it's a tree. So we don't want it, so it has no loops in it. So you pick a random one like that. And one nice thing about trees is you can walk across them in order and time, and then find a nice place to cut them into 2 graphs that are balanced, that have equal population approximately. So we pick one of the edges that would cut it equally, we cut that, and that then splits it in 2 because it's a tree, and we end up with 2 new districts. And you see that's a very global move. It looks dramatically different than the previous one, right? So that's a very nice way to do it too. But that also suffers from a problem that we don't know what distribution we're sampling from. We're just drawing some collection of districts. So these aren't what we want. And from the very beginning, in the earliest papers we wrote on this, what we've always advocated for is that we really want to first put a measure. Well, go back, Greg. I didn't want to flip yet. Stop, just stop. So we want to put a measure on the space of redistrictings. And we want that measure to be policy focused. So we wanted to capture in a transparent way through the policy issues. And then it's left to the mathematicians, the computer sciences, the computational scientists to draw a representative collection from that measure, which we can then use to do data analysis. And the interesting thing, I think this is a great example of what happens, in modern computational science and modern data science. This step of kind of drawing a representative collection or having a measure that we could probe on redistrictings wasn't possible until we had good computational methods, right? So it really lets us conceptualize the problem in a way that we couldn't do it before. So go ahead, Greg, next slide. So, okay, so now what we're gonna do is we're gonna, just to say those steps again that Greg showed before with a little more precision, we're gonna define a distribution that encodes the law and the possible redistrictions. Then we're gonna use some sampling method, Monte Carlos, Markov chain Monte Carlo, sequential Monte Carlo, enumeration something. And then we have to worry a lot. You can't skip the last step. You have to then do some good data analysis. And then not only that, but then figure out about how to transmit that information to the courts. And that's been one of the big jobs we spend a lot of time thinking about. All right, Greg. All right, so how am I doing? All right, we're doing okay. So Greg, yeah, yell at me if I start taking too long. All right, so how are we going to define this measure, this distribution? We're going to go ahead, Greg. So what we're going to do is we're going to put a distribution on all possible redistrictings of a state. And we're going to do that by putting a Gibbs measure. And we're going to pick a score function J, which is a sum of a bunch of different score functions. And we're going to then just stay there, Greg. Don't start going yet. No, just whoops, there. Stay there. I'll tell you when to go. So we're going to look at this thing, which is a sum of a bunch of different score functions. And it's important to have, it's good to understand the reason we choose this form is because this is actually the maximal entropy measure that if you had no other information except the information about what you would typically see for these different energy functionals, these different statistics, one for population, one for compactness, one for preserving counties, one for the Voting Rights Act, this would be the form of the measure. So now let's just go ahead, Greg, next slide. So let's see what the compactness score is. So the compactness score would just be some version of the isoparametric score, the area to the perimeter squared to the area. And then the next one, we might calculate the population as the deviation, the square deviation. And next slide, we also want to consider things like preserving communities of interest or satisfying the Voting Rights Act or county preservation. So there's all different choices here. And one interesting question is how much do these choices matter? And that's something we have to defend in court or in our work in general. All right, so now the question is, how do we sample this measure? So, all right, yeah, next slide. Okay, so to sample this measure, we're going to use a well-honed idea from computational statistics, from statistical mechanics, from computational physics, is the idea of the Metropolis-Hastings algorithm. And the Metropolis-Hastings algorithm is based on a simple idea. You can sample an arbitrary measure that you have access to using some other randomized algorithm for sampling. If you can modify the proposals from that original chain that you have so that it generates a reversible chain for this probability you're interested in. What I mean by reversible is that if you have two states, that's A on the left and B on the right, the flux from A, that is the chance of being in A and then moving to B, or the chance, which is mu B, of being in B and moving to A, if those fluxes are equal, then it's a quick check that you actually are sampling from the measure mu, okay? And so this is really an important, powerful idea, kind of the workhorse of modern Bayesian statistics. And we're gonna do this, but the trick is to do this, we not only have to be able to generate going forward the black arrow, but we also have to generate the orange arrow going backwards. So next slide, Greg. All right, so here's a whole bunch of different kinds of algorithms that we use. So there's, and I've kind of put them on the far left are just algorithms that are just random, and we don't know that much about them. And then ones in the middle where we have a better idea of what they're sampling. But the ones I'm going to talk to you eventually about are the ones we're using. And far on the right, the second one down, the top one, Metropolize, multiscale, forced recon. That's the method we've been using now, and that's the method that we developed that builds on the work of recon over on the far left. But the problem with recon is you don't know what measure it's sampling. All right, go on, Greg. All right, so what we have here is, okay, so this is a little bit technical, but the idea of the Metropolis force recon is actually sounds like a simple idea. instead of keeping track of partitions, we're going to actually keep track of spanning forests. That is to say, a collection of spanning trees, all right? And the reason we do that is, I'll show you in the next slide, don't go there yet, which is the most mathematical. And the reason to do this is that it's going to let us calculate both the forward and backward probabilities in a computationally feasible way. All right, so Greg, go ahead to the next slide. Oh, it's not, yeah, okay. It's the next slide, but let's just stay here for a second. So no, just stay there, that's good. So we're on this slide, so we can calculate this forward probability just the way I talked about it. Now go ahead, I think it's right here. Oh, not yet. Okay, now go ahead. So the trick is we want to be able to calculate this backwards or orange arrow. So we don't only want to be able to calculate the forward probability, we also want to be able to calculate the backwards probability. So the probability of starting on the lower right and going to the upper left, all right? And that's what this kind of metropolized forest recon modifies the recon algorithm in such a way that it makes this computationally feasible. So go ahead. And so the next slide is the overwhelming math slide, but let me just explain it to you. So the point is I want you to kind of, if you look at these bottom two parts, there's some metropolis thing, and on one side, on the left side, we're thinking about partition space, and on the right side, we're thinking about tree space. And the top one with this red arrow, what it points out is to go forward, there's a many to one deterministic map, then a one to many random map, then a one to few random map, and then finally a many to one random map. And the problem is that many to one random map is really actually a large number, many to one. And so the problem is inverting that map is very, very complicated to calculate the backwards probabilities. And by switching to just using a tree space representation, we remove that many to one map step at the end, which collapses a given tree to all the possible to a partition. And if you're going to invert that, you have to figure out all the trees that could have given rise to a certain partition. And that's very expensive. All right, so go on, Greg. So using that algorithm, so actually go back, sorry. Using that algorithm, we were able to really make it feasible to use metropolis Hastings. So now go forward, Greg. But still, it wasn't good enough. So what we ended up doing now is we actually wrote a multi-scale version of this. So, redistricting often happens at a very multi-scale way naturally. That is to say, states are divided up into things like counties or some kind of municipal regions. And then below that, they're broken up into precincts. And then those precincts might be broken up into census blocks and so on. So there's a very natural multi-scale structure. So what we're going to do is, instead of representing it like we do in the top plot there, where we have all this fine scale structure, we're going to instead say, like, if we keep a county whole, we're just going to think about keeping that county whole. We're only going to resolve structure where we need it to really define a map. And we found this really speeds up and makes computationally feasible things that were not feasible before. So go ahead, okay? So now a step of our algorithm is, this is kind of our multi-scale forest recon. So we're going to take two districts, the green and the dark gray. We're going to merge them together to create the light gray. Then we're going to draw a spanning tree at the coarsest level, which is the county level here. And then we're going to find a place to split it, and we're going to cut it. But now we're going to actually then refine inside those two places we're counting. We're going to actually draw another spanning tree that has the right boundary conditions, but that itself is a spanning tree inside of those two districts. And then we're going to find a place to cut it, and we'll cut it, and we end up at this final one at the far right. And the point is that in calculating these things, we need to calculate various determinants, and the kind of, which counts the number of trees. And so calculating this determinant, doing it in this multi-scale way, we save a lot, because each of the objects that we're calculating spanning trees on is a much smaller object, much smaller graph, by first doing this coarse graph and then moving down. So this is kind of a classic version of a multi-scale computational method having a big win. All right, Greg, next one. Is it time to pass it off yet? Not quite. So here's a movie of this multi-scale forest recon happening, and you see that it's refining in certain parts of the state wherever it's splitting, and the places that are being refined are moving around as the algorithm runs. This is, of course, not actually real time, but it's not so far off. If we're just generating, remember, but we're doing this extra step. We're then using Metropolis Hastings to accept, reject which has the added advantage of letting us know what distribution we're sampling from. And so the conversation can really be policy driven. All right, go ahead, Greg. All right, so the last thing was that that's actually not enough to do everything we want. So in doing this, we've actually been using an idea which is called parallel tempering, and we've explored simulated tempering also, but we mainly use parallel tempering. And the idea is this: if you look at this distribution in the gray box, it has a parameter beta, and there's also a gamma parameter that has to do with the number. Tau is the number of spanning force for a particular graph, for a particular partition. And so we actually have to calculate these two things, and the dependency on this creates some very deep wells in our potential. So what we actually find is that if we take beta equals 0 and gamma equals 0, which is the bottom of this stack of blue leaves here, we can actually sample very, very efficiently from that. But it's very hard to sample from beta bigger than 1 and gamma equal to 1, or even just beta bigger than 1. Forgetting about leaving gamma equals 0 is also hard in many contexts. Sorry, I have the hiccups all of a sudden. So what we do is we use an idea called parallel tempering. And so we run at each of these intermediate values. So this kind of red arrow going up is supposed to mean that each of these copies of our state of North Carolina are running at different values of beta and gamma that are interpolating from beta equals 0, gamma equals 0, all the way up to beta equals 1, gamma equals 1. And so what's happening is we're starting here, and we're at the bottom, and we're being able to switch. So, you know, a chain starts at the bottom and then it switches to the next level. Sometimes then it switches up, then switches up to the top, and then maybe comes back down. And there's a way to do this so that the measure at each of these levels is actually preserved. And so we're running this on some rather large machines, sometimes like some 40 core machines, to be able to, you know, make use of parallelization. And, you know, I should say that Fightfield and Inuma had a nice version of this, which is related to what we're doing, although slightly different. All right, Greg, go on to the next slide.
I'm going to take over for a little bit.
That's your chance. Take off.
Okay. So, you know, perhaps to overly stress it, but we're talking about it because we find it so important. There's been a lot of language in this field talking about kind of focusing on the ensemble of plans, focusing on the samples themselves. And I really wanted to take a moment to stress that the ensembles really are conduits of the measures, as Jonathan was talking about. The ensemble is a way to access information in the measure. And I just want to sort of go through a quick example of the danger you can get in if you simply talk about random plans versus kind of really thinking and really considering the measure. So let's suppose a plan is extreme with respect to a measure that does not preserve municipalities, but that it is not extreme with respect to a plan that does preserve municipalities. And I'll show you an example of this in a moment. The point is the following. The question then becomes, instead of the question becoming, oh well, this plan is an extreme gerrymander because it's extreme according to this ensemble, or it's not because it's not an extreme outlier according to this ensemble, the question becomes one of policy. It says, should we preserve municipalities or not? Or was the decision to preserve municipalities politically motivated? Or should we compare a plan to those that preserve municipalities or don't preserve municipalities? It takes what attempts to squeeze itself in as a statistical question and really turns it into what it should be, which is a policy-driven question. And so an example of what we see, you know, a very real example that we see in practice is this is the North Carolina State Senate so that there are 50 seats here. And this purple, these purple histograms come from an ensemble that does consider preserving municipalities. And these orange histograms come from an ensemble that does not consider preserving municipalities. And you can see that there are plans that could have been drawn that where you see sort of a plan from the ensemble that does preserve municipalities could be a complete outlier with respect to one that doesn't. In other words, there are regions of space that this accesses that the other one does not. It kind of tightens up as we come along, as we get into this region here, but over here, there are these kind of disjoint regions in space that one type of ensemble has access to and another one does not. Jonathan, I'm gonna hand it back over to you.
All right, go ahead. So Greg's point there is really important, that that we have always emphasized making this policy-driven thing, but the policies we've taken are usually the policies given to us by the court. The court said, we want to, make compact districts, or not the court, I mean the legislature. We want to make compact districts. We want to preserve counties. They usually give some guidance to the redistricting commission. Now, there's lots of things that people talk about when they talk about redistricting. They talk about proportional representation. They talk about things like that. So Greg, go to the next slide. So they invoke things like proportional representation. If one group gets 51% of the vote, they should get close to 51%. They represent symmetry. Go ahead. So they say like, oh, what happens to you should happen to me. I mean, that doesn't make it really make sense, given that one group might be more concentrated in urban areas and one group might not. Just looking at a core statistic doesn't really make sense. Next, maybe some kind of efficiency. People talked a lot about the efficiency gap at various times. There's various ways that's been discredited now, but still. So we've always said that you shouldn't really think about these things because they're not what the legislature laid out as the directive for when it goes to redistricting, right? But these weren't the goals thing. But it's an interesting thing. When it comes to this remedial phase, so what do we mean by remedial phase? That's law jargon for there's been a court case, there's been a ruling, and then there's a phase where everyone agrees on a remedy for whatever was found to be wrong. So in this latest court case in North Carolina and in other court cases, the court actually said, you know what, we're going to add some specifications to what should have happened. And in this most recent court case, it actually emphasized above all symmetry. It said, we actually want them to be symmetric. So they added this new wrinkle, which was interesting for us. So go ahead. I think the next slide, Greg, is that right? Oh, sorry, one more slide. So just to emphasize that if you just take this ensemble that only considers the compactness, equal population, the geography of the state of North Carolina in this case, but we've done this in other states, it doesn't actually give you proportionality. If it was proportionality, there's this black line, those histograms would fall right down the middle of this black line. So next time somebody says to you like, this election was totally unfair, this party got 52% of the votes or 50% of the votes and they didn't get 50% of the seats, remind them that the whole system wasn't designed for proportionality, right? But now what happened was there was this remedial phase, and interesting thing happened. The court actually added to the criteria that was supposed to be in play for a good map. So I think the next slide is the one I want. Is that right? Yes. Okay. So this is actually, this is a month old, right? This just went to this. If you heard about the Supreme Court of the United States ruling on a North Carolina case, it was the Supreme Court deciding that this ruling was okay for the moment, at least. They may still come back to it, but they decided not to intercede before the next elections. So the next elections will use maps that were created. So what happened? So the legislature was told that their maps were not okay. They had to create a new map. And they came back and produced a map which was this top one. So let me decode what this map says. What this map says is, how many seats did you get? That's the vertical axis. When you are in the majority, the red curve is the Republicans in the majority, the Democrats is the blue curve. And then as you had a certain majority with a certain percentage. So if you had just over 50% of the votes, the Democrats typically, under the map the legislature put forward, had just over 6 seats. And the Republicans had just under 8 seats. And then as the percentages move up, you see this go up. And this gray region is kind of the gap, the failure to be symmetric, all right? So what we then showed, well, you could pick some maps from our ensemble, not all of them, but once the court said we should worry about symmetry, we went back looking for symmetric maps, and they're actually maps that actually act rather symmetric. So this one below, so you see the heading is U.S. Congress to the far left column. Below that is the one that the plaintiffs actually put forward to show that the legislature could have done much better, right? It could have come up with a much more symmetric map, one that treated the two sides more fairly, more equally. And based on that and other arguments, you can't get in their head, you can't know what made them decide. They actually threw out the new map, the map that the legislature proposes a fix, and they sent a special master off to make a new map, okay? Unfortunately, the same was true of the map they put forward in the House, So the panel to the right is the same thing for the North. When we say House, we mean the North Carolina House. We have a Senate and a House, just like congressional. And the map at the top is the one they put forward. And the map right below it is one that we showed did a much better job of being symmetric. And the map just to the right, just showing you even just simple consequences. There was one longstanding effective minority district. So it was a minority opportunity district where in the northeast corner of the state, the African-American population had a good chance at selecting a candidate and had repeatedly been able to do so. And their choice of redistricting destroyed that. And we just undoing that destroying of it, it was easy to undo, was enough to actually make the map much more symmetric. And that's what this dotted lines are. So even, so the one to the left of it, the one right, bottom left-hand corner there under House, bottom left-hand corner, under House, bottom left-hand corner under House, there you go. That one is what you could have done. It's much better. But even if you just made a small change going to the right to protect that minority performing district, you would have actually already come up with a much more symmetric map. All right, Greg, I think, am I done yet? Almost. Okay, right. So there you go. So is this me or you? Me?
It's
okay.
you. Go ahead.
Okay, good. Sorry, we
We're just
split it up
wrapping
and I forgot how we
Yeah.
split this one. So I'm bringing us home, right?
Yep.
So I just, here you have, we're talking to the converted, we're talking to a bunch of data scientists, and computational scientists of various ilks and flavors. And so I'm just going to say that, here's an interesting problem that you're having a social justice workshop next week, right? And good math, I think good problems give good math. Don't switch yet, Greg. There's a whole bunch of good problems that are coming out of, ideas of trying to quantify, societal questions. And I think what's interesting about them is you can actually use them to change the conceptual framework, right? Political scientists, had an idea of fairness, but it wasn't one that they could implement, so we didn't really talk about it. But here we could say oh, let's just ask, here's the criteria. What would a map look like if we just use those criteria? That wasn't something they had access to. But we're oh, we can put a measure there and answer that question. And so that was something that the computational scientists could actually bring an entire reformulation of the problem to the table, which is interesting. And I think there's a lot of interesting possibilities to do that in problems that we haven't thought about, because now we're in this world rich with data. So there's so many examples of people doing stuff. So start the slide. So there's tons of them. So here's some work that was really pioneered by Maria, Alan, and Wes at CMU. And this is interesting for the computer scientists people in the room. Maybe it's very combinatoric. It asks, what can you say about testing the significance of an outcome, even if you don't know that the Markov chain is mixing? So it's a very interesting test. And then we kind of updated and adapted it to North Carolina, and I was part of that. Next slides. Right, this is actually a critical thing in the landmark case in Pennsylvania. Next slide, Greg. Here's an interesting paper by Fightfield, Keizuke, and their collaborators. This is also another interesting computer science paper. It uses kind of smart data structures to cache parts of a computation you've already done to make a large-scale enumeration feasible. So it's a very smart way to use the structure of the problem to actually let you enumerate, things that had like 40,000 plans, Greg? Or, something like that. So where you could really enumerate 40,000 things in a reasonable amount of time. And what's interesting about it is actually, so click it, Greg. We actually use this enumeration slide to the right as a validation of our sampling method in court. So we actually took an enumeration and brought a computational enumeration and brought it to court and said, look, here's one of the sub problems in our state in a small region that it breaks up in North Carolina into small regions. We said in this one, we could actually count all the plans and look at our sampling doing a good job. So you should maybe believe what we did. So we actually presented this in court, which is cool, right? So go on, Greg. There's tons of other stuff. There's a really nice sequential Monte Carlo algorithm that's building on some of our ideas in this multiscale one, but they've taken it in a different direction. It's really nice. There's lots of other people coming with different algorithms. There's some topological data analysis coming out of the Tufts group. There's some nice stuff on optimal transport and measuring, kind of trying to use it for geographic localization of these problems. Go on, Greg. Then there's lots of interesting ideas. So in this slide by this paper with Becker, Duchin, Gold, and Hirsch is another example of this. Like, hey, can we rethink what the problem should look like? So this is trying to assess Voting Rights Act compliance by thinking of the problem again from the beginning and saying, what's the embedded computational problem that we wished we could have solved? Let's actually go try to solve it, and then use that instead of maybe some kind of very qualitative statistics at a high level. So this is a really nice step forward there. And there's lots of other, the effects of the census using this. We did some other public policy work, providing an algorithm for the state to answer a question that the courts forced them to do, but they had no algorithm for it. The courts told them basically lay out a greedy algorithm, but they didn't know that. And so we were able to go actually write code for the state and make it publicly available. And so then in this most recent districting, this bottom left-hand thing, these were 2 high school students who worked with us. They actually, they used their code to start the redistricting process in North Carolina, because that's the first step, is finding the optimal county clusterings in North Carolina. Greg, next slide. There's lots of other people coming up with metrics and different ideas here, and other, different redistricting methods, like this you pick, I choose metric of Procaccia and Pegden and you. Go on, Greg. And let me just end with kind of, since, we're speaking at a university here. I mean, kind of. Sorry, we're not actually speaking at a university. Thank you anyway for inviting us. But one thing we found really interesting about working in this field is that it's been a great place for undergraduates to participate. So all the people with UG next to them are undergraduates. It's master students too. So it's been a great way to involve them in research. And also we found that these problems really can, if you bring a team together, they bring a really diverse group of team together in all ways you can imagine. Diverse as in what departments they came from: computer science, economics, social science, statistics, math, all together. Diverse in their backgrounds, diverse in their interests, diverse ethnically, diverse gender, every way, because it's a question that appeals to a broad slice of our culture. And so it's been a great thing for undergraduates to work on. So the way I got into this was this very first woman at the top, Christy Vaughn, now Christy Vaughn Graves, who this was her sophomore summer project that we did. And it grew into this whole enterprise. And so it's wonderful. I really recommend it. As if you're at all curious, get in a group of undergrads together and try it for a summer, try something, out of your social justice hackathon, whatever, right? I think it's a great thing to do. I should also mention that not everyone wants to fund things like this. So I should thank the Polis Center and the Information Initiative, which is our data science center at Duke, and our provost office and our deans for generously supporting this work at times when maybe other people weren't. And then I'll say that there's a website, Quantifying Gerrymandering, you can go to, and we regularly post things there, like a recent analysis we just did of Georgia. And I think that's all. The last slide says thanks, right? With a movie, because God, I love these movies. I'll just say these movies are fantastic. When we play them in court, it's really a lesson on how a good visualization, everyone in the court pays attention. Like there were people who were like online shopping, reporters and other people, I could see them doing it. And then we show one of these movies and everyone just is transfixed. It's a little jerky by Zoom. In person, it's a little better, but it really, we've learned a lot about, like, you say like, well, here's this thing, can't you see it? And yeah, you as a data scientist, like it's obvious to you because you've looked at 100 like projections onto principal component analysis bases, and what this RQ curve means, and and all this stuff, and then you show it to the courts and they're like, what the hey, go away, right? Part of getting them to listen to us in the beginning was really kind of finding the language, and I should say that the lawyers have helped us a lot. We've had really great luck with having some fantastic law partners who have taught us a lot and really brought us forward. So anyway, so with that, thanks for having Greg and I here.
Yeah, so let's go ahead and thank the speakers.
Thanks a lot.
Yeah, and so with that, are there any questions for Greg? I guess, Jeff, you have your hand up?
So great talk. I'd love to tie together the math and the modeling and the visualization, all that, and then the legal stuff. So the question I had is, so, you know, if you're sampling using MCMC, you don't, you know, one of the downsides of it is you don't know if the process has converged, at least not necessarily. So did this ever come up in court? Did you have to convince people that that you're actually drawing from the sample, or did you convince them that without ever getting into those sort of details? I'm curious
there's
about
there's lots of answers to that question. And when you say you don't know, what I think you mean is that you don't know. I mean, and what I mean by that is you as a computer scientist or a mathematician don't know. But if there are lots of well-established tests, right? I mean, people use MCMC sampling in quantitative Bayesian statistics all the time, right? Every time you like get flagged as a credit card alert that your credit card has not been paid, somebody's run some Markov chain Monte Carlo sampling thing probably in the background, and to a point where they feel consistent that and then it works really, really well, right? So there's a whole bunch of ideas like Gelman, Rubin. So what we do is we do a whole bunch of independent samples, and then we compare important. So first of all, we don't need the whole chain to converge. We only need the marginal statistics we care about to converge. So we can then compare the distribution of those marginal low dimensional marginals, and we actually check that. All right, so there's evidence that there's problems, but then we can also show empirical evidence. So in court, we often have shown, you know, pretty convincing empirical evidence that our distributions have converged. So we do show that in court, and we also show robustness. Right, so I mean, right, there's not a theorem yet, and there's some theorems that say that if you want to do the whole distribution, you might actually have a hard time, and that it's NP complete. But we also know that there are plenty of NP complete algorithms that we use all the time with great success, because our problem instance space isn't the worst case problem instance space that the NP complete statement is about, right? Every computer scientist knows that NP completeness is a dangerous, sometimes a red herring, right? I mean, you know, think about simplex method and how that's supposed to be horrible, but yet we run our whole world on it, right? Right, and interior point methods, right? So you know, I think that you know, I think that's part of the answer. The other answer is that often those details don't come up directly in court. They're happy to see that we've done robustness checks. They're happy to see that we've made modifications to the measure. That being said, though, increasingly, like, you know, if you know, the court case is about, did you damage my car? And then you show the picture of the car, and the car has been lit on fire with gasoline and rolled over with a semi-truck, then it's kind of like every kind of measure that you would use to decide if the car has been damaged will probably answer that the car has been damaged, right? But increasingly now we're getting more subtle, right? The questions are becoming more subtle. It depends more and more what measure. In the beginning, the reason a lot of people just said random measures, random samples, is because it mattered less, right? The answer to the question didn't matter much. It was so dramatic. But as things go forward and we get more nuanced and we're kind of moving to the edges of this, I think you need to be more principled and say, like, yes, we're sampling from a measure which is not only constrained to be like previous maps, but is actually validating, valorizing. It's putting significance, weight on the maps that capture the policy issues we're interested in. Sorry, that was a really long answer, but there were
great.
lots of parts to that question.
Yeah. Thanks.
Greg, do you want to add anything to that?
No, that was pretty thorough.
Sorry. I'm turning red, if you can see.
Any other, maybe one last question, or?
I have a question. So we did in Utah, we did a lot, an effort to have community members draw community interest maps. And so now the input is not just some measure, but it has a lot of error and uncertainty and whatever from the contributions. From
one second. I don't necessarily agree with your statement, right? I mean, like in Michigan, they had a lot of community of interest maps put in, but you could put those into the measure.
Right. So that's my question: is how do you put something into the measure where there's a community defining different communities of interest that have some amount of overlap and some amount of uncertainty
Right.
in how they define those.
So in Michigan, the MGG at Tufts did a nice job of kind of pulling out a whole bunch of maps that people put forward and creating some similarity scores. So you can imagine creating some vector of similarity between different districts. Like how much should this district be in the same, how much should this precinct, I misspoke, I meant to say precinct. How much should this precinct be in the same district, right? Like, you know, if a whole bunch of people put these things together in a community of interest, then you might hope that you could draw maps that clump those together, right? And you could very easily then make an ensemble, a measure on those ensembles that put weight on maps that kept those communities of interest whole, right? We do that in a very generic way when we think about keeping cities whole. So like we look at a city and we say like, what fraction of the people are not with the rest of the municipality who could have been? Like this city could have fit in one district, and yet you took 15% of this district and city and put it in another district. Or this district city could have been in 5 districts, and yet you spread it across 7 districts, right? So we do that in our problems, right? We actually have a measure of how it fractures municipalities, and you could have easily extended. We do that with minorities, Hispanics, and African Americans, depending on the state. But you could also think about other communities of interest, right? And it would be most useful if the policy conversation started to be a little more, give a little more specificity. I'm not saying they have to write down an energy, but they have to say, we would like maps that keep these communities of interest that are found in this way whole, right? Chris, does that help?
Yeah, absolutely.
Did I touch on, or did I get off your question?
Well, yeah, I think the key was to convert it to some sort of probability measure.
Yeah, so I mean, you know, that's what we think, that's how we think about it. I think the reason we like that is it splits the question into 2 parts. It says, here's a measure which everyone can argue about, critique, you can impeach me because of my choice of measure, right? And then there's a separate conversation, which is, let's sample from this. And we can use our method, you know, Kezuki can use his method, you can use lots of different methods, and, you know, and then there can be validation, right? Right? And it does a nice job of kind of separating those 2 conversations, which I think is conceptually important.
I think that's good, because there was a lot of discussion here about like how do you weight when you've got multiple, you know, conflicting policies,
Yeah.
How do you weight all that kind of stuff. And
so someday I hope that our
separate.
Michigan stuff will see the light of day. We kind of ran into a wall of having 7 weeks to do 7 months worth of work for North Carolina, and had to kind of stop everything else for a moment.
Cool. So maybe in the interest of time, we can kind of cap there and maybe stop the recording. And I guess thank our speakers one more